Steel shapes the modern world. It delivers stability, safety, and structural integrity across industries that define contemporary life. From transportation networks and industrial machinery to renewable energy systems and advanced manufacturing, steel remains indispensable. Today, it is far more than a traditional construction material. It is a precisely engineered, high-technology product. At Salzgitter Flachstahl, steel production begins with iron ore sourced globally. Raw materials arrive by ship and rail from Scandinavia, Canada, South America, Africa, Australia, and beyond. The feedstock includes lump ore, fine ore, and pellets. Compact spheres formed from iron ore concentrate, optimized for handling efficiency and stable metallurgical performance inside the blast furnace. The Salzgitter site operates multiple blast furnaces dedicated to hot metal production. The largest stands more than 50 meters tall, equivalent to a 15-story building, and can produce up to 14,000 tons of hot metal per day. Inside the furnace, alternating layers of coke, iron ore, and fluxes are charged from the top through a rotating distribution system. Preheated air at approximately 200 degrees Celsius is injected into the lower section. As oxygen reacts with coke, processed gases reaching temperatures near 2000 degrees C are generated. These gases reduce iron oxide, removing oxygen, and enabling metallic iron to form and melt. After about 8 hours, molten iron and slag accumulate in the hearth. Every 2 hours, the tapping process releases liquid iron at roughly 450 degrees Celsius, while slag is separated. The hot metal is transported in torpedo ladle cars to the steel plant. In the steelworks, hot metal is converted into crude steel using LD converters. Each converter has a capacity of approximately 220 tons. Pure oxygen is blown through a top lance and bottom tuyers, oxidizing carbon and unwanted elements. Scrap steel is added to control temperature peaks that could otherwise exceed 3000 degrees C. The refining cycle lasts around 40 minutes. At this stage, crude steel is produced, with daily output reaching up to 500 tons. Secondary metallurgy refines chemical composition according to customer specifications. Alloying elements such as manganese, silicon, chromium, nickel, titanium, and molybdenum are added to achieve specific mechanical and corrosion-resistant properties. Continuous casting transforms liquid steel into slabs up to 35 centimeters thick and weighing as much as 32 tons. A solidified shell forms while the core remains molten before final solidification and cutting. Most slabs are transferred to the hot strip mill. Reheated to approximately 250 degrees Celsius, they are rolled in reversing roughing stands and then in finishing stands to produce strip up to 2,000 meters long. Coils are formed at the end of the rolling line. Part of the production is supplied to Ilsenberger Grobleck for heavy plate manufacturing, including wind energy tower components. Cold rolling further reduces thickness to between 0.35 and 3.0 millimeters at speeds approaching 90 kilometers per hour. Subsequent processes include annealing, temper rolling, electrolytic galvanizing, and hot-dip galvanizing at approximately 450 degrees Celsius. Organic coating lines apply protective and decorative finishes tailored to automotive, construction, and packaging applications. An integrated power plant recycles process gases to generate electricity and steam, maximizing energy efficiency. Continuous research and collaboration ensure ongoing product and process optimization. Steel remains fully recyclable without quality loss, reinforcing its role as a sustainable, high-performance material for future generations. In modern metal processing, competitive advantage is defined by precision, process control, and the intelligent use of advanced technology. Whether slitting steel or aluminum coils, cutting sheet metal to exact lengths, or delivering fully packaged products, every stage demands engineered accuracy and disciplined execution. High-performance slitting lines utilize precision ground knives, automated positioning systems, and real-time tension control to ensure clean edges, minimal burr formation, and consistent strip width. Material integrity is preserved throughout the process, maintaining mechanical properties critical for downstream fabrication. In cut-to-length operations, leveling systems equipped with multi-roll precision technology eliminate internal stresses and restore flatness to exacting standards. Digital measurement controls maintain tight dimensional tolerances, ensuring each sheet meets specified thickness, width, and length requirements. Surface quality is carefully protected to prevent defects that could compromise forming or finishing operations. Customized solutions further enhance efficiency. Production parameters are tailored to customer specifications, including special coatings, protective films, and packaging configurations designed for safe transport and storage. Skilled technicians oversee every operation, supported by rigorous inspection protocols and traceability systems. From raw coil to finished, packaged product, the entire workflow is integrated to deliver consistent quality, structural reliability, and performance-ready material for demanding industrial applications. At Accieri di Caliotto, the vision to recalibrate the future, starting today, is translated into measurable technological advancement. The rolling mill integrates digital traceability, advanced automation, and precision forming systems to deliver high-performance wire rod for demanding industrial applications. Production begins with billets ranging from 140 times 140 millimeters by 9, 500 millimeters to 160 times 160 millimeters by 7,009, 500 millimeters, with individual billet weights between approximately 350 and 850 kilograms. The plant processes a broad spectrum of steel grades: low, medium, and high carbon steels, case hardening grades, cold heading steels, quenching and tempering grades, spring steels, boron steels, and welding wire qualities. With a production capacity of 70 tons per hour, the facility operates under integrated Level 1 and Level 2 automation systems, ensuring synchronized equipment control and real-time process optimization. Standard rolling covers diameters from 4.5 to 26 millimeters, while the newly implemented loop enables thermomechanical rolling between 13 and 26 millimeters, enhancing mechanical properties through controlled deformation and temperature management. The MEER Drive Plus system, combined with a 4-pass sizing block, guarantees dimensional precision and surface quality. Finished wire rod products, from 4.5 to 26 millimeters diameter, are managed through a QR code tracking system, curved roller conveyors with protective hoods, an RDS rotating system, and a V-type pallet transport and discharge system integrated with H-hook coil handling. A calibrated weighing system ensures complete traceability and quality assurance throughout the process. A chain is only as reliable as every link within it, and at PWAG Group, that principle defines the entire production process. Manufacturing begins with precisely cleaned wire, cut and bent to exact dimensions under tightly controlled parameters. Each link is formed and welded with uniform energy input to eliminate structural inconsistencies. Following welding, every chain undergoes calibrated heat treatment to achieve the required hardness, toughness, and fatigue resistance. Surface finishing, whether sandblasted, electro-galvanized, or coated, enhances corrosion protection. Final inspection includes bending and breaking tests to verify load capacity, ensuring certified strength, traceability, and dependable performance worldwide. In mining, a single spring failure can halt an entire operation, so performance is engineered long before the first load is ever applied. Manufacturing begins with certified high-grade alloy steel selected for controlled chemical composition and mechanical performance. The hot coiling process is executed within calibrated temperature ranges to maintain grain structure integrity. Immediately following forming, springs undergo precisely monitored quenching and tempering cycles. These heat treatment stages are controlled through advanced thermal systems to achieve the required hardness, tensile strength, toughness, and elastic recovery while relieving internal stresses. Shot peening is applied to all springs to induce beneficial compressive surface stresses, significantly improving fatigue resistance and extending operational life under cyclic loading. Dimensional accuracy, load rate, and deflection characteristics are verified through calibrated compression and load testing equipment. For corrosion resistance, protective systems such as electrostatic powder coating or electrolytic treatments are applied, depending on environmental exposure requirements. Steel production changes the moment a limitation is challenged. At Emirates Steel Arcan, continuous innovation drives the evolution of heavy section manufacturing. The company supplies a comprehensive portfolio of structural products, including beams, channels, and sheet piles, serving infrastructure, marine, energy, and construction sectors across global markets. As demand patterns shifted toward higher volumes and tighter performance tolerances, process optimization became a strategic priority, particularly in sheet pile production. Historically, sheet piles were rolled using beam blanks as feedstock. This approach represented a practical compromise for limited production runs because the existing continuous casting machine was configured to produce billets and beam blanks only. While technically feasible, converting an H-shaped beam blank into a Z profile required removing the two flange wings before progressive rolling could refine the geometry. The transformation demanded multiple rolling passes, increased deformation energy, and imposed additional thermal and mechanical stress on the steel's microstructure. Such a route is inherently inefficient for large-scale output. Repeated rolling cycles elevate operational costs, extend production time, and create variability in metallurgical consistency. Microstructural strain accumulation can also influence grain flow orientation and mechanical performance, requiring tighter downstream control to maintain specification compliance. Recognizing these constraints, Emirates Steel Arcan advanced the development of a slab casting methodology tailored specifically for sheet pile production. By introducing a plain rectangular slab format as the starting geometry, the rolling sequence becomes significantly more streamlined. The slab eliminates unnecessary material removal and reduces deformation complexity, allowing for optimized pass design and improved dimensional accuracy. This innovation enhances throughput, lowers energy consumption per ton, and strengthens metallurgical integrity through more uniform deformation patterns. The result is a technically superior, economically efficient manufacturing pathway, positioning Emirates Steel Arcan at the forefront of heavy section mill process engineering and high-performance sheet pile production. In heavy structural fabrication, strength begins long before the first weld arc ignites. At Steel Bricks, HD fabrication represents a disciplined approach to building high-definition structural components engineered for demanding load conditions. Thick steel plates arrive at the facility and move through precision cutting systems where CNC plasma and oxyfuel technology shape each element according to exact digital drawings. Dimensional tolerances are verified immediately, ensuring downstream fit-up accuracy. Edges are beveled and prepared to optimize weld penetration and fusion integrity. Assembly takes place on rigid fabrication beds designed to control distortion. Components are aligned using calibrated fixtures before multipass welding begins. Heat input is monitored to manage shrinkage and residual stress, particularly critical for heavy box sections and complex node connections. Where required, automated welding systems deliver consistent bead geometry and repeatable deposition rates across long seams. Post-weld operations include mechanical straightening, surface grinding, and detailed inspection. Non-destructive testing, such as ultrasonic or magnetic particle examination, confirms structural soundness. Surface preparation follows with blasting to specified cleanliness standards. Every stage is documented for traceability, from raw material certification to final inspection reports. The result is HD fabrication, defined not only by scale, but by dimensional precision, weld quality, and structural reliability. High-performance seismic fabrication demands absolute welding integrity, and the Arcman structural steel welding robot system from Kobe Steel limited answers that requirement with a fully integrated automation platform. Designed for structural steel applications requiring AWSD 1.8 compliance, The system utilizes FCAW wire MX50R to deliver consistent, high-quality welds in demanding seismic connections. Operation begins with intuitive workpiece setup and clamping. Fabricators input workpiece data through a user-friendly interface, enabling precise remote control and seamless production flow. Once initiated, the robot employs wire touch sensing to accurately detect weld seam positions, ensuring exact joint alignment before arc ignition. During baseplate welding, the arc remains stable and controlled, generating minimal spatter and clean bead profiles. The integrated positioner automatically rotates the workpiece to the optimal welding orientation, improving penetration consistency and reducing operator intervention. When slag forms, the system performs automatic tool changing, switching from welding torch to slag removal device without interrupting workflow. Additional automation features enhance reliability and repeatability. Wire is automatically cut to the optimal stick-out length, while nozzle and torch cleaning cycles maintain arc stability. Stiffener welds exhibit excellent arc control, and shear plate welding proceeds, with uniform heat input and bead geometry. By integrating welding, sensing, cleaning, and slag removal into a unified robotic cell, ArcMan significantly improves productivity, weld consistency, and compliance with stringent seismic fabrication standards. In structural steel fabrication, efficiency is engineered into every movement. The TBL beams welding line from Nuova CMM is designed to transform individual plates and webs into perfectly welded I-beams through a synchronized, automated sequence. Steel plates move into position. The web settles onto the infeed line, forming the spine of what will become a structural member built for serious load demands. On the Nuova CMM TBL beam line, every stage unfolds with mechanical precision. The side lifting arm engages first, raising and guiding the flange into alignment against the web. A controlled tack weld locks the geometry in place, just enough to secure stability before the assembly advances. The partially formed T-beam rolls forward into the welding station, where automation takes control. Self-adjusting rollers recalibrate instantly to match section dimensions, keeping the beams centered and fully supported. As the welding heads travel along the joint, arc stability remains steady, delivering deep fusion and a smooth, uniform seam along the entire length. Thermal input inevitably introduces stress, but the integrated straightening module compensates immediately. Pressure is applied with calibrated force, restoring linear accuracy and eliminating distortion before it compounds. The welded member transitions onto the discharge conveyor, maintaining uninterrupted production flow. Hydraulic tilters rotate this section with controlled torque, repositioning it for the next operation. The infeed arm opens once more, this time to introduce the second flange. Alignment is verified, contact is secured, and the final welding pass completes the transformation. What began as separate plates now stands as a fully assembled I-beam, balanced, rigid, and dimensionally precise. From initial placement to final weld, The TBL system orchestrates each motion with industrial discipline, converting raw steel into structural components ready for bridges, buildings, and heavy infrastructure. Steel bridge fabrication has entered a new era with the introduction of the Endeavor Gantry drilling system. From FICEP.weld shrinkage and dimensional variation, further complicated automation, making precision drilling of long bridge girders a persistent challenge. The Endeavor Gantry drill overturns that conventional workflow. Instead of conveying girders through a fixed drilling line, the welded member remains stationary while the gantry travels along its length. This dramatically reduces required floor space and eliminates the need for extensive entry and exit conveyors. Once positioned on the gantry bed, advanced laser scanning probes all relevant surfaces and end locations. The system automatically adjusts the part program to match the actual geometry of the welded girder, compensating for shrinkage and fabrication tolerances with digital accuracy. Equipped with direct drive 31 kilowatt spindles delivering full motor power at speeds up to 5,000 RPM, the machine performs drilling, milling, tapping, and countersinking using high-performance tooling. A 6-position automatic tool changer on each spindle increases flexibility, while a 200 mm sub-axis enables simultaneous processing of flanges and web even when hole patterns are not aligned. Capable of milling holes over 50 mm in diameter, preparing web bevels, and scribing attachment locations, the system removes manual layout entirely. Available in processing envelopes up to 4 meters wide and 1.8 meters high, the Endeavor Gantry drill handles large, heavy, uniquely shaped weldments that defy traditional conveyor lines. The result is measurable labor savings, higher precision, and a transformative impact on bridge fabrication productivity. When gear diameters reach 4 meters, machining demands more than capacity. It demands absolute control. The LC4000 from Liebherr is engineered specifically for large-scale gear hobbing and profile milling in heavy industry. Designed to machine workpieces up to 4,000 millimeters in diameter, the LC4000 delivers the rigidity required for high torque cutting while maintaining micron-level precision. Its robust machine bed, thermally stable structure, and powerful drive systems ensure consistent performance under extreme loads. The swiveling hob head enables flexible machining of complex gear geometries, while CNC-controlled axes coordinate synchronized motion for accurate tooth generation. Beyond traditional hobbing, the machine supports profile milling within the same setup, reducing repositioning time and improving concentricity. Heavy-duty table capacity accommodates massive slewing rings, wind turbine gears, and mining components. The result is a platform where scale meets precision, purpose-built for the largest gears in modern power transmission systems. Few manufacturing programs demand the level of dimensional control and metallurgical discipline required by the Utter Organization vacuum vessel. Hyundai Heavy Industries has finalized the first of 9 vacuum vessel sectors required for the Utter tokamak. The procurement of the vacuum vessel is shared by Europe and Korea. For the inboard segment, production begins with inner shell forming, shaping thick stainless steel plates into precise curvature. FSH hole machining establishes critical port interfaces, followed by electron beam welding on the FSH structures to ensure deep, defect-free fusion. IW's rib welding reinforces structural stiffness under extreme electromagnetic loads. In the upper segment, both outer and inner shell welds are completed before precision FSH hole machining and intermodular key welding. Phased array ultrasonic testing verifies weld integrity, while remote visual examination confirms surface compliance. Final machining restores tight tolerances after welding distortion. The equatorial segment integrates inner shell fabrication, FSH modeling and machining, and FSH welding. IW's ribs and blocks are installed to enhance rigidity. Outer shell fabrication and welding follow, culminating in final machining and comprehensive 3D measurement validation. Sector assembly completes the sequence. Upper segment installation, splice plate fit-up, transfer to FAT facilities, and final helium leak testing, confirming vacuum integrity essential for fusion operation. For the lower segment, electron beam welding joins heavy sections before shell machining. TRs and T-rib installations strengthen load paths, followed by turnover and outer shell welding. In the assembly pit of ITER organization, precision meets scale. 1/9 of the vacuum vessel is carefully lifted from its tooling and lowered into position over a meticulous 2-day operation. Sector module number 8 now joins modules number 6 and number 7, forming nearly half of the plasma chamber. The complex maneuver once again validates the metrology system's accuracy and the coordination of the rigging team. 3 additional heavy lifts are scheduled to complete this critical phase of reactor assembly. Manufacturing of the Haven 1 primary aluminum structure is in full motion at vast space. Raw aluminum plates undergo orthogrid CNC machining, inspection, precision rolling, automated welding and trimming, forming a structural cone and a 3.8-meter cylinder, entirely designed, built, and validated in the United States. For the first time in decades, a primary space station structure is being manufactured entirely in the United States. At vast space, HAVEN1 represents more than hardware. It signals the next chapter beyond the International Space Station. At the center of this effort is the full-scale qualification article, built to validate strength, safety, and structural performance. Production begins with raw aluminum slabs, precision cut using high-pressure water jets. Panels are then CNC machined to achieve exact structural geometry before being rolled into curved sections that form the backbone of the station's primary shell. Each weld is executed and inspected to aerospace standards, ensuring alignment, integrity, and repeatability. Once complete, both halves are carefully mated and joined through a final structural weld, creating a unified pressure vessel. The structure is then painted, outfitted with its domed window and hatch, and shipped to Mojave for qualification testing, where it must withstand pressures exceeding 22 psi, meeting NASA STD-5001 requirements and clearing the path toward flight hardware production. At Gap, the Parco Rotami is engineered as an integrated, digitalized scrap management system designed to optimize efficiency, traceability, and production control within steelmaking operations. Internal recycling streams are centrally coordinated to ensure continuous material circulation back into the production cycle. Scrap entry management begins at the gate, where incoming loads are identified, classified, and registered through automated control systems. The basket transport system then moves charged scrap containers through predefined logistics routes, minimizing idle time and ensuring precise sequencing. A dedicated basket weighing system guarantees accurate mass measurement before furnace charging. Each basket load is digitally recorded through computerized load management, enabling full traceability and real-time data synchronization with production planning systems. Silage management ensures controlled storage and blending of scrap grades, optimizing chemical composition consistency. Extraction systems regulate material withdrawal according to melting schedules. Ferroalloy handling, including storage, movement, and discharge, is executed with strict monitoring protocols to preserve material quality. Continuous stock control and productivity factor analysis provide operational transparency. Routine yard cleaning and organized material flow maintain safety standards, reinforcing a highly automated, performance-driven scrap park infrastructure. At the rolling department of Kaiser Aluminum Warwick operations, transformation begins the moment a cast ingot arrives. The surface is first scalped, top and bottom layers precisely shaved to remove imperfections and ensure a clean metallurgical foundation. The ingot is then preheated in one of two pusher furnaces, conditioning the aluminum for controlled deformation. Hot rolling starts at the reversing mill, where 44,000 pounds of aluminum pass repeatedly between massive rolls driven by 7,000 horsepower motors. At roughly 900 degrees Fahrenheit, thickness is reduced from 21 inches to 1.5 inches, while length expands dramatically. The continuous mill refines it further before coiling. Cold rolling follows, bringing final gauge accuracy measured in thousandths of an inch. When oversized flanges demand precision without the option of disassembly, field machining becomes the only viable solution. At Stalcon, large diameter flange resurfacing is executed directly on site using the powerful Climax portable machine tools CM6200 portable circular mill. Engineered for heavy industrial applications, the CM6200 handles flange diameters ranging from 2 500 millimeters up to an impressive 6 500 millimeters. Mounted securely to the existing structure, the machine establishes a rigid cutting platform capable of restoring flatness, parallelism, and surface finish to exact tolerances. This eliminates costly transport, minimizes downtime, and preserves alignment within large assemblies, such as pressure vessels, turbines, or offshore components. During operation, the rotating milling arm sweeps across the flange face, with controlled feed rates and stable torque delivery. The result is uniform material removal and a clean, concentric sealing surface ready for reassembly. Even at extreme diameters, dimensional accuracy is maintained through careful setup and calibrated adjustment. By combining portability with industrial-grade rigidity, Stalcon delivers high-precision flange machining exactly where it is needed, on-site, under real-world conditions, and without compromise. The Hyundai Kia KBN 135 is a heavy-duty CNC horizontal boring and milling machine engineered for precision machining of large, complex components. Built on a massive cast-iron foundation with rigid box guideways and pre-tensioned ball screws, this machine delivers both structural stability and high cutting accuracy, attributes that make it a workhorse in energy, heavy equipment, and industrial fabrication facilities. At its core is a 135 mm diameter spindle drive with a high-torque 3-step gear system and Cat 50 taper, capable of generating strong cutting force at speeds up to 2,000 RPM. Linear and rotary scales on all axes provide real-time feedback, enabling ultra-precise positioning of both tool and workpiece during operations such as deep boring, contour milling, and fine finishing. The W-axis travel of 700 mm and X/Y per Z travels of approximately 3,000 mm/2,000 mm/1, 600 mm allow the machine to process substantial workpiece envelopes without repositioning. Control is typically provided through advanced CNC systems, enabling multi-axis coordination and complex machining patterns with repeatable accuracy. The 2000 x 1/800 mm work table supports up to 10,000 kg of load, making it suitable for heavy castings, large housings, and structural components. Integrated features like through-spindle coolant and automatic tool changers enhance productivity by reducing non-cutting time and enabling continuous operation. In high-precision machining environments, this platform bridges the gap between brute force and refined control, delivering the robustness needed for deep cuts and the precision essential for critical fits. Its design reflects decades of industrial machine tool development, where rigidity, accuracy, and versatility are equally paramount. The circular seam milling machine from Miba Automation Systems is engineered for precise weld seam preparation in heavy fabrication. Designed to process large cylindrical components, the system achieves milling depths up to 150 mm on wall thicknesses, reaching 180 mm. It accommodates workpieces up to 12 meters in length, ensuring exceptional flexibility for demanding industrial applications. The result is accurate seam geometry, improved weld penetration, and consistent preparation quality for high-integrity structural assemblies. In modern heavy fabrication, precision is no longer a competitive advantage. It is the baseline. What separates industry leaders from the rest is intelligent automation. That is where PIMA steps in, redefining how complex steel structures are built through advanced automated welding and production systems. Inside a high-capacity fabrication hall, massive structural components move with calculated rhythm. Positioners rotate multi-ton assemblies into optimal welding orientation. Gantry robots glide along linear tracks with measured authority. Every movement is deliberate, digitally coordinated, and synchronized through integrated control architecture. This is not simply welding mechanized. It is welding engineered. PEMA's automated solutions combine robotic welding cells, column and boom systems, and adaptive positioners into unified production lines. Advanced seam tracking and arc monitoring technologies continuously adjust parameters in real time, compensating for distortion, heat input variation, and joint tolerances. The result is consistent penetration, uniform bead geometry, and repeatable quality across long production runs. At the heart of the system lies intelligent data management. Welding parameters, heat input, travel speed, and deposition rates are logged and analyzed to ensure compliance with stringent structural codes. This traceability is critical in industries such as wind tower manufacturing, offshore structures, pressure vessels, and heavy steel assemblies where weld integrity directly impacts structural performance. Automation also transforms productivity. Multi-axis manipulators allow simultaneous welding on multiple joints. Integrated roller beds and fit-up stations reduce non-value-added handling time. Automated tack welding, root passes, fill passes, and final cap layers are executed with program precision, minimizing operator variability. Skilled personnel shift from repetitive manual tasks to oversight, programming, and quality validation, elevating both efficiency and workforce value. Perhaps most significant is the scalability of PEMA systems. Modular production cells can expand into fully automated lines, accommodating growing throughput without sacrificing control. Whether fabricating large-diameter monopiles for renewable energy or complex box girders for infrastructure, the system adapts to geometry, thickness, and material grade. In a market defined by tighter tolerances, higher strength steels, and relentless schedule demands, automated welding is no longer optional. It is strategic infrastructure. Through integrated robotics, digital monitoring, and engineered production flow, PEMA transforms heavy fabrication from labor-intensive craftsmanship into precision-driven industrial performance. The future of structural manufacturing is not louder or faster. It is smarter, cleaner, and uncompromisingly consistent. From an empty stretch of steel yard to a 71-meter giant commanding the skyline, This is the 40-ton double girder gantry crane brought to life by Henan Guanhui Crane. Designed for heavy steel coil handling in open yard conditions, this crane is built for scale, strength, and endurance. Every plate begins its journey under strict dimensional control, cut precisely according to engineered production drawings. Internal stiffeners, leg supports, and structural welds are fabricated under disciplined quality standards, because in heavy lifting, precision is non-negotiable. Inside the workshop, sparks fly as the main girder takes shape. Weld seams are executed for deep penetration and structural continuity, then polished to ensure surface integrity. Camber detection verifies alignment across the full 71-meter span, confirming that geometry meets exact specifications before assembly moves forward. The crane legs undergo verticality testing and diagonal inspections to guarantee balance and symmetry. Skilled technicians pre-assemble the end carriage, install the wheels, and integrate the long travel drive system with meticulous attention to mechanical alignment. Windproof armature systems are fitted to secure stability in exposed environments. As the legs are positioned and angles adjusted, the main girder rises, hoisted with controlled precision into its final position. Every connection is measured, every tolerance verified. Then comes the moment of truth, comprehensive safety and load testing. Systems respond, structures hold, performance is confirmed. From tailored design to final commissioning, this 71-meter gantry crane stands as a statement of engineered strength, built not just to lift, but to endure. Few rotating components command more respect than a 214-megawatt steam turbine rotor. This particular unit is especially rare, integrating the high-pressure, intermediate pressure, and low-pressure sections onto a single continuous shaft. The result is a massive, highly engineered assembly, where dimensional accuracy and balance are absolutely critical to operational reliability. During outage service, field machining restores critical journal and coupling surfaces without removing the rotor from site. Portable machining systems are aligned directly to the shaft centerline, re-establishing concentricity and correcting wear or minor distortion. Every cut is controlled to micron-level tolerances to ensure proper bearing contact and seal performance once reassembled. Following machining, low-speed balancing is performed to verify mass distribution before the unit returns to high rotational service. The rotor is mounted and rotated at approximately 60 RPM, allowing technicians to measure vibration signatures and identify imbalance vectors. Correction weights are calculated and applied with precision, minimizing dynamic forces that could otherwise amplify at operating speed. Generator testing completes the sequence, validating alignment, coupling integrity, and overall system performance. When dealing with a combined hydrogen phosphide IPLP rotor of this scale, every adjustment carries consequence. Precision in setup, machining, and balancing ensures that once steam is admitted, the rotor delivers stable power, smooth, controlled, and ready for continuous generation.